Now in this last video we're going to be looking at something called Kirchoff's laws, but before we do that I want to sort of revisit the battery here. In the past videos we've been assuming our batteries have been ideal batteries. That is, if you put them in a circuit and you measure the voltage across the battery, you would get in this case 1.5 volts, sort of regardless of how much current you're actually drawing out of the battery. Well, for real batteries that's not really true. A real battery has a circuit model. That's what engineers call our ideas about how components work. They call them circuit models. So our circuit model of a battery looks something like this. So there's my picture of a battery, my D cell. And inside would be some chemicals that would generate a certain voltage as those chemicals react. And we represent the voltage of the chemicals by a little battery symbol. And we call this voltage sort of script E. And script E stands for EMF, which itself stands for electromotive force. Now, electromotive force is not really a force. It's the voltage of the chemicals inside the battery. And remember, voltage is a joules per coulomb thing. Now, in series with this sort of hypothetical voltage generating chemical battery inside the actual D cell is a resistor. And that resistor represents the resistance of the chemicals themselves. So the chemicals do two things. They generate an EMF, but they also have a resistance to the current flowing through the battery. In fact, as the battery ages, as you sort of use it up, the resistance of this resistor gets bigger and bigger and bigger. The resistance of the chemicals gets larger and larger and larger until it gets so large that when you try and draw current out of a battery, there's a larger and larger voltage drop across that resistor. And that means the effective voltage between these 2 points, the 2 terminals of the battery, starts to drop to zero, because this voltage drop becomes so high because of the increased resistance due to the aging or use of the battery. Now, we actually call the voltage that we measure between the 2 terminals of the battery, we call that terminal voltage. And again, the terminal voltage of a battery depends on the circuit that you actually put the battery in. If you draw a lot of current out of the battery, your terminal voltage is going to drop because of this internal resistance. More current that you try and draw out of the battery, the bigger the voltage drop here. Okay? As the battery ages, that resistance gets bigger and bigger and bigger, and therefore the terminal voltage across the battery in the same circuit is going to start dropping as the battery ages. Okay? So this is going to be the circuit model that we're going to be using as a model for our batteries in the coming calculations. And this will be a good way of introducing the concept of Kirchoff's laws by using this model for a battery. So just to recap here, electromotive force, not really a force, it's the voltage of the chemicals in the battery. Batteries have an internal resistance. That internal resistance increases as the battery gets used up, as the chemicals in the battery get used up. Okay, so what I'd like to do is analyze a circuit that consists of these real batteries as opposed to our sort of phony ideal batteries. And that circuit is going to be composed of 2 batteries that are in series with one another. And we're going to use our little circuit model here where we have a battery that consists of an electromotive force. I'm going to call that E sub A because this is going to be battery A, and it's 1.5 volts. And then it has a equivalent resistance here. Call it R sub A. And I'm going to make this a pretty good battery. It's pretty new, so the resistance is fairly low, 1 ohm. And these things together are one of my batteries. And now here's another battery, again consisting of an EMF, which I'm going to call E sub B, which is also 1.5 volts, but it's a pretty old battery. So this resistance of the chemicals, we're going to make that 20 ohms. Notice the EMF hasn't changed very much, even though it's an old battery. A battery to its dying day will have about the same EMF as it has when it's brand new, because it's just there's less chemicals to react, but it still has the same electromotive force. It's this resistance that increases as a battery ages. Okay. So I'm going to have this battery pack be pushing current through just an external resistor here. I'm going to call that R. And the direction of the current is going to be coming out of the plus side of the battery. And it's going to be kind of going around like this. Call that I. And it comes around through here and goes through the external resistor. And then it comes around, goes back into the second, or the first battery I should say, and goes right on through the battery in one continuous loop. Now as this current moves through this circuit, it's going to get voltage boosts because of each one of these EMFs of the battery that it moves through, the current moves through. But there's going to be voltage drops associated with the internal resistances of each battery. And it turns out that all the boosts and all the drops going around a loop like this are all going to add up to 0. And we call that law Kirchoff's loop rule. And really it's just a statement of the conservation of energy. If I have this pen, say for instance, and I raise it up and I move it around and then I put it back to where I started, the change in gravitational potential energy of the pen will be 0 as long as I start and end at the same level. Well, in a similar vein, if I go around a loop, as long as I start and end at the same point in the loop, all the changes in potential energy have to add up to 0, and that's what Kirchoff's loop rule really says. How you use this rule is first you draw a direction for your loop. Now I can actually go either way. I can go backwards or forwards to the loop. It doesn't matter. I like to try and make my loops to the maximum extent possible go in the same direction as the current. But you don't have to. But I'm going to do that for this example. Now, as you go around the loop, anytime you go from the minus end of a battery to the plus end of a battery, or the minus end of an EMF to the plus end of the EMF, that will be a positive voltage change. That will be a boost. And anytime you go in the same direction as the current through a resistor, that will be a voltage drop. Now, if I were to draw the loop backwards, if I go backwards through an EMF, in other words, I'm going from the plus side to the minus side, that would actually be a negative voltage change. That would be like a voltage drop. And if for some reason I draw my loop so I'm going in the opposite direction of the current flow through a resistor, that would actually be a voltage boost instead of a voltage drop. So going against the current through a resistor makes for a voltage boost rather than a voltage drop. And if you go backwards through an EMF from positive to negative instead of negative to positive, that will give you a negative voltage change, which would be like a voltage drop. Okay, so in applying Kirchoff's loop rule, I'm just going to start here. It doesn't matter where you start in the loop. And I'm going to go in the direction of the loop that I drew in green here. So going through the EMF here for battery A, I'm going from minus to plus, so that would be a voltage boost, going from minus to plus. So I'm going to call that plus 1.5 volts. Okay? Now, when I go through the resistor here, the 1 ohm resistor associated with battery A, since I'm going in the direction of the current, this will be a voltage drop, and that voltage drop will be equal to the resistance times the current. So this is going to be minus I times 1 ohm voltage drop. I get another voltage boost going through EMF for the battery B, because again I'm going from minus to plus, so that is a voltage boost. So that's 1.5 volts of voltage boost. In a similar vein, going in the direction of the current I through the second battery resistance is a voltage drop. So minus I times the value of that resistor, which is 20 ohms. Continuing around the loop, I have another voltage drop here associated with the external resistance. So that's going to be minus I times R. And now I'm back to where I started. So that I've gone once around the loop, and all of these things should add up to 0 by Kirchoff's loop rule. Okay? So what I need to do here is I want to solve here for I, total current going through the loop. So I add these two voltages together and I get 3.0 volts plus. And then I have factor out a minus I out of 1 ohm plus 20 ohms. I forgot to give R a value. Let's make R 100 ohms. And so this is now 100 ohms. And we'll have plus 100 ohms here. And all of that's equal to 0. And so now I can solve for I. I is equal to 3.0 volts divided by, well, adding all these resistances together, that would be 121 ohms. And when I work that out on my calculator, I get 0.0248 amps. That would be the current going through my circuit here, going through both batteries and also through the external resistor. Now I can actually now figure out what the voltage is going to be across each battery. Okay, so remember the terminal voltage encompasses both the EMF and the resistor. So if I wanted to find out what the voltage was across, let's say, this first battery, it would be equal to the current going through the battery times 1 ohm would give the voltage drop here. And if I add that voltage drop to the EMF, that would give me my battery terminal voltage. So let's do that. So for battery A, call that bat A, V terminal across the two terminals of the battery is going to be equal to the electromotive force, that's my boost I get from going from there to there, minus the drop, which is equal to I times R sub A. So that would be 1.5 volts EMF minus my current, which I now know to be 0.0248 amps, multiplied by the resistance, the internal resistance of the first battery, which is 1 ohm. And when I work that out, I get 1.48 volts. Okay, so it's not quite 1.5 volts anymore because of the drop in voltage due to the internal resistance. And I can do the same thing for battery B. Battery B, V terminal, electromotive force for B minus I, R sub B is equal to 1.5 volts minus 0.0248 amps, but this time it's going to be 20 ohms of internal resistance because it's an old battery. And when I work that out, I get 1.00 volts. That's quite a bit of drop from 1.5 volts that the battery had probably when it was new. Okay, another thing I'd like to point out is that if I were to measure the voltage across the entire battery pack in this example, it would be 1.48 plus 1 volt, which would be 2.48 volts. So actually a full half a volt less than what I might expect if I naively expected the voltage across both batteries in series to be 1.5 plus 1.5 or 3 volts. Because this battery is old, its internal resistance is fairly high, and that causes a pretty decent drop of terminal voltage across the battery pack of two batteries when I put it in a circuit. Okay, the next example I want to do is of two batteries in parallel, real batteries as opposed to sort of idealized toy batteries. So here's my first battery. This is battery A, and it consists of an electromotive force, 1.5 volts, same as before, an internal resistance of 1 ohm, same as before. And now this is in parallel with another battery whose EMF, call it EMF B, is still 1.5 volts, but its internal resistance, because it's an older battery, has gone up to 20 ohms as before. So we've got two batteries in parallel, and they're both hooked up to some external resistance R, like that, and R is equal to 100 ohms as before. Okay, so we're going to use Kirchoff's loop law, but we're also going to use another law called Kirchoff's node rule. Kirchoff's node rule, or node law. And basically what it says is that the sum of the currents going into a junction called a node going into the junction is equal to the sum of the currents coming out of the junction. So if I have two currents going into this point, you add them together and that equals the current coming out. So the first thing I want to do is make some assumptions about which way the current is flowing. Well, it makes sense that current would flow out of these batteries. And so you have a current kind of going this way and a current going that way. Let's call this current I sub A. And let's call this current I sub B. Current kind of going through internal resistance A and internal resistance B. And then these currents kind of merge together and make a total current coming out, which continues around the circuit. Continues around the circuit. Continues around the circuit. And then it goes back into this node here, where it splits up into I sub A and I sub B again. Okay? So Kirchoff's node rule is applied to this node would be I sub A plus I sub B, that's the currents going into the node, is equal to the total current coming out of the node. And that same equation applies to this node here. It's just you kind of flip it around. Now you have I total going into this node, and that's going to be equal to the sum of I sub A and I sub B coming out of the node. Okay, something else that needs to be said about Kirchoff's node rule, and that it's equivalent to the idea of conservation of electric charge. You can't create or destroy electric charge, and since current is just the flow of electric charge, that means that the flow of electric charge going into a given point on a circuit must be equal to the flow of electric charge going out of that point if you're not to destroy or create electric charge. So Kirchoff's node rule, conservation of electric charge; Kirchoff's loop rule, conservation of energy. And let's go ahead and apply the loop rule to this circuit. There's actually 3 loops in the circuit as opposed to the single loop in our last example. One of the loops goes around inside this part here. Another loop kind of comes around like this and goes to the top resistor, but not through the bottom, and goes around like that. And then the last loop goes through the bottom resistor, kind of like this. So I'm going to look at the a loop going through this portion of the circuit here. So I'm going to draw in a direction for my loop. It doesn't matter which way I go. You can go clockwise or counterclockwise through this loop. I'm going to go clockwise. And applying the loop rule, let's say starting here, as I go up in the direction of the loop, I go in the positive direction through the battery. I go from minus to plus. So that would be a voltage boost of 1.5 volts. As I go through the resistor, I am going in the direction of the assumed current I sub A. And as long as I'm going in the direction of the assumed current, that would be a voltage drop through the resistor. So I'm going to make this minus I sub A times 1 ohm, the value of that resistance. Continuing along the loop, I'm now going in the opposite direction of the assumed current I sub B through through this resistor. And if I go through the opposite direction of the assumed current, instead of a voltage drop, it's actually a voltage boost. So I'm going to call this plus I sub B times 20 ohms. And then continuing around, I'm going backwards through the battery from plus to minus. So that would be a voltage drop instead of a voltage boost. So that would be minus 1.5 volts. And all that has to add up to 0 by Kirchoff's loop rule. So what I'd like to do here is sort of solve for I sub A in terms of I sub B. The 1.5 volts are going to cancel out. I can put I sub B and I sub A and the I sub A term and I sub B term on opposite sides of the equal sign. And what I get when I do that is I sub A is equal to 20 times I sub B. So I'm going to put a box around that because I'm going to need that later. And I'm also going to put a box around this equation because I'm going to need that later. Okay, the next loop I want to do is this outer loop here going through the top resistor. So it looks something like this. Coming around, going through the top resistor, and then coming back around like so, kind of in this direction. And let's go ahead and do the loop rule for this guy. Let's start here at this point and again go through the battery, or the EMF I should say, plus 1.5 volts going in the proper positive direction. Another voltage drop here, minus I sub A times 1 ohm. Coming back through here, another voltage drop down here, which would be minus the total current times 100 ohms. Again, I'm going in the direction of the assumed current, so it's a voltage drop. And that's about it. I get 2 drops and 1 boost, and all of that's equal to 0. And when I solve this for I total, what I get is I total is equal to 0.015 amps minus I sub A divided by 100. The amps come from the fact that I'm going to have 1.5 volts divided by 100 ohms during that solution. And a volt divided by an ohm is an amp. And here I have an ohm that's going to be on the top and an ohm that's going to be on the bottom that are going to cancel out. So I'm kind of adjusting the units a little bit in addition to solving for I sub total. Okay, now I have that equation. I'll go ahead and put a box around it. What I can do is I can set this I sub total equal to this I sub total. And I get I sub A plus I sub B from this equation is equal to I sub total from this equation, which is 0.015 amps minus I sub A divided by 100. And what I'm going to do here is I'm going to combine some terms, getting all the I sub B's together on one side and all the I sub A's together on the other side. And when I do that, I get I sub A times 1.01 plus I sub B is equal to 0.015 amps. I guess I put them both on the same side there, okay? Where this comes from is I'm just moving this over to the other side, factor out the I sub A, so that'll be I sub A times 1 plus 1 over 100, which is 1.01. Add that to I sub B, and that's equal to 0.015 amps. Now what I'm going to do is I'm going to take this expression for I sub A equal 20 I sub B and substitute that into here. And when I do that, I have 20 I sub B times 1.01 plus I sub B is equal to 0.015 amps. And kind of combining terms here, that gives me 21.2 I sub B is equal to 0.015 amps. And that implies that I sub B is equal to 0.015 amps divided by 21.2. And that's going to give me 7.07 times 10 to the minus 4 amps. I'm going to put a box around that. Okay. Now, I realize that if I multiply that by 20, that'll give me I sub A. So coming over here, I sub A is equal to 20 times I sub B, which is 7.07 times 10 to the minus 4 amps. And when I do that, I get an I sub A of 0.0142 amps. Put a box around that. And finally, I know that I total is going to be the sum of I sub A plus I sub B, which is going to be 0.0142 amps plus 7.07 times 10 to the minus 4 amps. And I add those two together and I get 0.0149 amps, and that becomes my I total. Now, a good check to see if I've done my math right for these different currents is to verify that the voltage drop across this resistor is going to be equal to the change in voltage between these 2 points, which is going to be equal to the change in voltage between these 2 points. Because all these points lie along the same wire. I'm just taking the voltage difference from one side of the circuit to the other side of the circuit, and no matter how I do that, that voltage change ought to be the same. So let's start down here with a 100 ohm resistor. The voltage change or voltage drop across that 100 ohm resistor is going to be equal to the current times the resistance. That current is equal to 0.0149 amps, and if I multiply that by the actual value of the resistance, which is 100 ohms, what that's going to give me is 1.49 volts. So I'll put a box around that. The voltage drop across that resistor. If I want to figure out what the voltage change is between these 2 points, which is just connected by a wire, so it should be the same, that's going to be equal to the voltage boost minus the voltage drop. So in this case, this is going to be 1.5 volts minus the voltage drop of I sub A, and I sub A is equal to 0.0142 amps. 0.0142 amps. Times the value of the resistor, which is 1 ohm. And I work that out, and I should also get 1.49 volts. Same voltage as I got down here. If I do it on this bottom part, now I'm going to have my voltage boost, which is 1.5 volts, minus the voltage drop across this resistor, which is going to be equal to I sub B, which is 7.07 times 10 to the minus 4 amps, times the value of that resistance, which is 20 ohms. And when I work that out, I should also get 1.49 volts. And I encourage you to do that on your calculator and verify that all of these, in fact, are all equal the same number of 1.49 volts. A good check on my work. I'd like to say one more thing about Kirchoff's laws, both the node and the loop law. In order to use these laws, you have to make some assumptions about the direction of the currents, and you can kind of use your common sense to figure that out. But it turns out it doesn't matter how you make those assumptions. For instance, let's suppose I assume that current I sub B was going in the opposite direction when I drew in that current. You'll still get the correct answer, It's just that when you solve for I sub b in this case, you would get a negative number, which means that whatever your assumed direction of the current was when you solved the problem, the actual current was moving in the opposite direction. Now if we look down here, we're going to find out that all the currents that I solved for were all positive, which means that my assumptions about the direction of the current were correct. But no big deal if you don't make the correct assumption about the direction of the current. You'll still get the right answer. It's just that you may get a negative value for that particular current. In a similar vein, when I'm using the loop rule, it doesn't matter which way I run the loop, either clockwise or counterclockwise. As long as I'm consistent with my rules about my change in voltage will be positive if I'm going across a battery in a direction that takes me from the negative end of the battery to the positive end of the battery, that would be a positive value for my voltage. And as long as I also make the caveat that if my loop carries me in the opposite direction of my assumed current, when I'm going across a resistor, that resistor in fact would represent a voltage boost rather than a voltage drop. So as long as I'm careful about all my signs for everything, it doesn't really matter which way I make my directions for my assumed currents or which way I make the loop run when I'm doing the loop rule.